This week the subject is special relativity. That's the second part of chapter 20. So here are the sections in chapter 20. The final three sections, 4, 5, and 6, are about relativity. This is called special relativity. That's not including gravity. The theory of relativity, including gravity, is called general relativity. Start with a little history of the theory of special relativity. It was developed by Albert Einstein in 1905. And it was related to electricity and magnetism. Before Einstein, it was believed that electric and magnetic fields were some sort of stresses and strains in a mysterious medium called the ether. Even Maxwell used the ether idea to help him drive some of the field equations. Now, Einstein developed the theory of relativity based on Maxwell's electromagnetic field theory. But the theory of special relativity denies the existence of this mysterious medium, the ether. In Einstein's theory, the reality is the fields, and there's no underlying medium. The fields just exist in their own right. Now, other scientists were working on similar ideas, similar to Einstein, like Lorentz, Fitzgerald, Heaviside, Poincaré. But Einstein developed the best theory because he rejected the ether hypothesis. So I guess I said this before. Before relativity, scientists believed that E and B are stresses and strains in some, I wouldn't say a substance, some medium called the ether, which supposedly fills all of space. So we and the Earth and the solar system were all surrounded by the ether. That was the theory. And then Maxwell's theory would describe electromagnetism in some preferred frame of reference, the frame of reference in which the ether is in equilibrium. That is to say, in which there is no motion in the ether, it's just in equilibrium, and there were stresses and strains. And those described the fields. Those were described by the fields. Well, Einstein rejected that. There were some experiments at the time that Einstein was developing the theory of special relativity, first few years of the 20th century, the Michelson-Morley experiments. The Michelson-Morley experiments were made in America. Michelson and Morley were both Americans working in America, and they wanted to show, their goal was to show or to measure the speed of the Earth with respect to the equilibrium state of the ether. But the result of their experiments was that the speed of light is the same in all inertial frames. That's that 299.8 million meters per second. And that completely contradicted the ether hypothesis, because that would the speed of light under the ether hypothesis would be different for frames of reference moving with different speeds through the ether. Well, the Michelson-Morley experiments showed that the speed of light is the same in all inertial frames, at least all inertial frames connected to the Earth, in all directions of motion. They were looking for a difference in the speed of light for different directions, which would indicate the direction of the Earth moving through the ether. But it was a null experiment. It was a null result. They found there was no variation in the speed of light. And that contradicted the ether hypothesis by experiment. Now, Einstein probably did not know about these American experiments when he was working on his theory. I think it's a little bit unclear whether he knew about the experiments or whether he just wasn't aware of them or didn't really realize their importance. So he just assumed by theory that Maxwell's equations are valid in all inertial frames. So by that theoretical assumption, the speed of light, I'm talking about the speed of light in empty space, c, would have to have an universal value, because Maxwell's equations would hold in every frame of reference. And Maxwell's equations calculate the value of c. So c would have to be the same in all frames of reference. So apparently Einstein started with this assumption based on the theory. Maybe not even being aware of the Michelson-Morley experiments. So in Einstein's approach to the theory of special relativity, there were two postulates. The first postulate is called relativity. It says that the laws of physics are the same in all inertial frames. In other words, an observer measuring the laws of physics in let's say, the frame of reference of the Earth, and a second observer measuring the laws of physics in a moving frame, moving relative to the Earth, perhaps moving in a spaceship. Well, of course, there weren't any spaceships in the time of Einstein. Einstein would say moving in a railroad train. Those two observers would obtain the same experimental results, indicating that the laws of physics are the same in the two different reference frames. So for two arbitrary reference frames, the laws of physics are the same, or the laws of physics are the same in all inertial frames. Now that actually is not so much an original idea of Einstein's. That's actually a very old idea. That's an idea that goes back to Galileo. Galileo believed that relative motion does not change the laws of physics. But Galileo was only considering mechanics. And Newton was considering electromagnetism, Maxwell's field theory, which of course didn't exist in the time of Galileo. So Einstein had a second postulate, the absolute speed of light. The speed of light, we're talking about light in empty space, because the speed of light changes in materials, but the speed of light in empty space is the same in all inertial frames. And that's kind of required by the fact that Maxwell's theory calculates the speed of light. Maxwell's theory, if we assume it's the same in all inertial frames, that means the speed of light must be the same in all inertial frames. Now, I think I've said this before. Postulate 2 implies there is no ether, Because if there were an ether, then the motion of an inertial frame relative to the ether would necessarily change the speed of light. If there was an ether that undergoing stresses and strains, producing electric and magnetic effects, the speed of light would have to be different for different speeds relative to the ether. Now, let's look at some of the results in the textbook. So let's start with section 4. That's called Relativity of Time and Space. Einstein's theory in 1905 was very revolutionary. What's so revolutionary about special relativity? Well, for Einstein's postulates to be true, time and space measurements must be different in different inertial frames. That's completely contrary to classical Newtonian physics. So here's a picture from the book. This is figure 20.9. It shows two inertial frames and two observers. So Sharon and Sam occupy different reference frames. Sharon is in a train. Sam is sitting on a couch on the surface of the earth. Sharon is moving with velocity v along the train track. Let's call this the x direction. So Sharon and the train are moving in the x direction. And so Sam is sitting here at rest on the earth. He sees the train coming towards him, going past him, then going away from him. The train is moving relative to the earth. Now, Sharon will make measurements using clocks and watches for time and rulers for distances. And those will be the measurements in her frame of reference. Her frame of reference, we'll call it frame F sub t. So a certain frame of reference, F sub t for train. Sam will make measurements on the same events using watches and clocks in the Earth frame of reference. So we'll call that frame of reference F sub e. The clocks and watches that Sharon has and the clocks and watches that Sam have are identical. And the rulers that Sharon has are identical to the rulers that Sam has. But Sharon's clocks and rulers are moving relative to Sam's. And that will result in different measurements using those apparatuses. Let's start with time dilation. Comparing times measured by the two observers. So we'll derive the results for time dilation. So as I say, F sub e, let's make this a little better. F sub e is the rest frame of the Earth. That's what Sam will measure. Sam will measure time and space coordinates using his clocks and watches and rulers. So he'll have these four coordinates for any event. For any event that he observes, It'll occur at some time, and he'll use his watch to record the time, and that'll be t. And it'll occur at some position, and he'll use his rulers to determine the position, the coordinates x, y, z. Now the frame f sub t is at rest with respect to the railroad train. So it's the rest frame inside the train. Also outside the train, but in particular, it's moving relative to the Earth, co-moving with the train. Sharon, using the same kinds of apparatus that Sam has, will measure the positions of this event, the coordinates of this event. It's the same event. The same event will be observed by Sharon, and she'll assign a time t0 and coordinates x0, y0, z0 based on her apparatus. I guess I already said this. The velocity of the train is v I hat. I hat is the unit vector in the x direction. V is the speed. V vector is v times I hat. So the train is moving relative to the Earth. Now we'll consider inside the train a pulse of light. The pulse of light, let's put it here, there's a flash of light. It starts here, and it's received here. So there's a flash of light that starts here, and let's call that the origin. So we'll call that point the origin. So x0, y0, and z0 will be 0, 0, 0. It's at the origin. And let's call that the time t equals 0. So that's the initial time, t equals 0. Now the light will travel up to this receiver, and then it'll be received. It'll be received at some position relative to Sharon, 0h0. So this distance is h. So this source of light and this receiver are attached to the train. So they're moving along with Sharon. Sharon is not moving relative to those two events. You know, she'll measure the radiation of the flash of light at the point 0, 0, 0 and at time 0. And she'll measure the reception at a later time and at the coordinates 0h0. So this is the position of the receiver in the frame of reference f sub train. Now, how long will it take for the pulse of light to go from this source to the receiver? Well, it'll be the distance divided by the speed of light. The distance divided by the speed of light. So it'll be h divided by c. So the time when it's received here will be h divided by c. Now let's suppose that at R there's a mirror. then the pulse of light will reflect from the mirror and come back down to the original point. So let's say this is the source of the light at this point. Well, let's make it 1 point. So there's 1 point here. And that point, we'll call that point P. That point is both the source and a receiver. So it has a little light source, like a light bulb, and it also has an electronic eye, which, when it receives light, it will make a click or something. It'll make some sort of observable event. And these are the same point. So this is actually the point where the mirror occurs. This is the point where the reflected light is received. Those coordinates are 0, 0, 0, because it's back at the original point. Relative to the train, in the frame of reference of the train, the light just goes up to the mirror and reflects back down to the original point, P. So the pulse of light travels to the mirror and back. The coordinates will again be 0, 0, 0. But the time will now be 2 times h divided by c. The flash of light has traveled a distance of 2h. H plus h. So the total distance is 2h. The speed of light in Sharon's frame of reference is c. So she'll receive that signal at 2h divided by c. So we can say the change in time for the coordinates 0, which are the coordinates of the train, the time coordinate of the train, will be 2h divided by c. All right, so we'll consider this 2 events. The first event is when the flash of light occurs. The second event is when the seeing eye, the electronic eye, makes a signal that it's received the pulse of light. And Sharon will have that measured time difference between the 2 events. These are 2 events occurring at the same point. Of course, the light traveled first to the mirror and then back to the reception point, but that's the same point, P. So there's no change in position between these 2 events for Sharon, because she's moving along with this source and receiver. And she will measure the time as 2h over c. Here's another picture from the book. In Sharon's frame, the light travels to the mirror. That's called D in the book, but that's called H in my calculation. And then back to the same point. It has a path of 2h. So this is what I would call 2h. And so the time will be 2h over c. Well, it should be 2h divided by c. Now, what about the same two events as observed by Sam? In Sam's frame of reference, the two events do not occur at the same point. Let's say that the origin of the train and the origin of the Earth coincide at time 0. So Sam's time measurement will start at 0, 0, 0. So in other words, the coordinates measured by Sam for the radiation of that pulse of light will again be 0, 0, 0, 0, as measured by his rulers and his clocks and watches. Now, the light will travel to the distance h, reflect from the mirror. Now, the mirror will have moved because the whole train is moving and the mirror is attached to the train. So the train will have moved, and so the mirror will be at a different position, a different x position. Remember, we're saying that the velocity is in the x direction. It'll reflect from the mirror, and it'll come back and be received at that same point P, which will be at a different position now. So the light path is longer in Sam's frame. The light is emitted at time 0, and at position 0, 0, 0, it reaches the mirror at some time tau. I don't know what time it is, but I'll figure that out later. At a position x times tau, because the train has moved v times tau. I should have said position x equals v times tau. And a position y equals h. So this is when the pulse of light hits the mirror. Z is not changing. Now, so that's when it hits the mirror, but that's not what Sam is measuring. What Sam is measuring is when is it received by that receiver at the base of the train car. Well, that'll be 2 times tau. For the time, this is 1 tau, so here's tau, and here's 2 times tau. So the time when it's received will be 2 times tau. And the x-coordinate will be v times 2 tau, or 2v times tau, because this point has moved at velocity v for a time 2 tau. In other words, it's moved by a distance 2v tau. Now it'll again be at y equals 0 and z equals 0, because it's come back down. This is the y direction. Well, it's come back down to y equals 0, as measured by Sam. But it's moved in the x direction. Now, in Sam's frame of reference, light travels at the same speed, c. So the distance that the light traveled will have to be c times tau. Well, let's just calculate the distance that the light travels from time 0 to time tau. So this time, the distance traveled will be v tau in the x direction and h in the y direction. So if I look at this little right triangle here and apply the Pythagorean theorem, delta x is v tau, delta y is h. So the distance was v tau squared delta x squared plus h squared, delta y squared, square root. So tau, the time for the light beam or the pulse to go from the source to the mirror, will be the square root delta x squared plus delta y squared. That's v tau squared plus h squared. That's the distance. That's got to be the speed times the time. The speed of what? The speed of the light. The light has traveled this far in a time tau. So this distance must be the speed times the time. Speed of what? Speed of light. And the speed of light is the same in all inertial frames. So that's again c. Now if I look at this equation, I can rewrite it as an equation for h squared. H squared is c squared tau squared minus v squared tau squared. So it's c squared minus v squared times tau squared. So these are Sam's measurements. In other words, in terms of Sam's time, the time measured by Sam's watch, delta t will be 2 tau. That's the time for the light pulse to travel from point P to the mirror and back to point P. 2 tau. So we had delta t0 is 2h over c. And delta t is 2 tau. I can use this equation for tau, take the square root of both sides, divide through by the square root of c squared minus v squared. 2 tau is 2 times h divided by the square root of c squared minus v squared. So they're different. The time measured by Sharon will be different from the time measured by Sam. They have clocks of exactly the same design. Their clocks work in exactly the same way. But they've measured the time between two events, the pulse being released and coming back, and they found 2 different times. And that's called time dilation. So let's write an equation for delta t in terms of delta t0. Delta t is 2h. Now 2h is c times delta t0, so the 2h is c delta t0 divided by the square root of c squared minus v squared. Or I can divide both numerator and denominator by c, so I'll have dt0 on the top. I'll have 1 minus v squared over c squared on the bottom. This factor, 1 over the square root of 1 minus v squared over c squared, is encountered often, so it's given a special name. That's called gamma. Gamma is by definition 1 over the square root of 1 minus v squared over c squared. It's something that depends on the speed of the relative motion. And so delta t is gamma delta t0. And that follows from Einstein's postulate that the speed of light is the same in all inertial frames. Okay, so here are the equations for time dilation. I hope you're taking notes because you're going to need these for the ln kappa problems. Delta t, that's the Earth frame of reference, is c times delta t0 over the square root of c squared minus v squared. where delta T0 is the frame of reference of the train. Or I can write that as gamma delta T0. And you're going to need to remember gamma. 1 over the square root of 1 minus v squared over c squared, where v is the relative speed is the relative speed of the two inertial frames. Now, gamma is always greater than 1, because 1 minus v squared over c squared will be a number less than 1. And if you divide 1 by a number less than 1, you get a number greater than 1. So gamma is always greater than 1. So dt is larger than dt0. So for example, if Sharon measured the time interval as 1 second, well, of course, 1 second would be an awfully long time for a pulse of light to travel from the base of the train to the top of the train, back to the base of the train. But just for the sake of argument, let's suppose dt0 is 1 second. Then dt will be gamma seconds. Gamma times 1 second. It will be gamma seconds, and gamma is greater than 1, so it will be more than 1 second. That's why it's called time dilation. What's the meaning of the word dilation? Well, it comes from the verb dilate. Dilate is an intransitive verb, which means become wider or larger. So when you dilate your pupils at the ophthalmologist, your pupils get wider. They're dilated. Well, the time here is dilated. It's longer. Now, Sam, looking at the results, Sharon goes to the train station, comes back, and tells Sam that pulse of light took a time of 1 second. And Sam will say, no, that pulse of light took a time of gamma seconds. Sam will say Sharon's clock is running slow. You should have measured gamma seconds, but you only measured 1 second. Your clock must be running slow. So Sam will say that Sharon's clock is running slow. But Sharon's clock is perfectly ordinary. Sharon's clock is not broken. Sharon's clock is in perfectly good shape. It's just that the time intervals are different in the different inertial frames. Time dilation leads to something called the twin paradox. What's the twin paradox? Well, here I've copied this from Wikipedia. In physics, the twin paradox is a thought experiment in special relativity involving identical twins, one of whom makes a journey into space at a high-speed rocket and returns home to find that the twin who remained on Earth has aged more. Here's one of the twins. We could call him Sam. Here's the other twin. We could call her Sharon. Sharon leaves the Earth at time 0, comes back 5 minutes later, and Sam says, no, it's 25 minutes. It's been 25 minutes. Or let's say this clock measures hours. So she comes back 1 hour later, according to her clock. But Sam has aged by 25 years. So Sam says, your clock is running slow. But not only is your clock running slow, but your aging process is running slow because you're only 1 year older than when you left. But me, I'm 25 years older than you when you left. So the twin who remained on Earth has aged more. Why is it a paradox? It appears puzzling, because each twin sees the other as moving. So it's an incorrect paradox. It says that Sam will say that he's aged more, but if we viewed it this way, if we said, well, Sharon is at rest and Sam is moving, going away and coming back, she should say, well, I've aged by 25 years and Sam is only aged by 1 year, analyzed in her frame of reference. So each should, that's where the paradox comes in. Each should paradoxically say, or find the other to have aged less. Well, they can't both have aged less than the other. The paradox is resolved by saying that the frames of reference are not the same. Sam is at rest on the Earth. That's an inertial frame. Sharon is traveling in a rocket. She's accelerating away from the Earth. She reaches some point, she decelerates and stops and comes back. In order to come back, she has to decelerate until her velocity is 0. Then she has to re-accelerate until she comes back to the same velocity and arrives at the Earth. So she has a period of acceleration. An accelerating frame is not an inertial frame. Inertial frames have constant relative velocity. But a frame that undergoes acceleration is not an inertial frame. Now, which one is undergoing acceleration relative to the universe? Well, Sharon is undergoing the acceleration because she has to slow down and stop and come back. So her frame of reference is not the same as his frame of reference. His frame of reference is the inertial frame, so he is the one who has aged 25 years, whereas in her inertial frame, her non-inertial frame, she's only aged by 5 years. So, as it says here, the traveling twin is undergoing acceleration, which makes him, well, it should be her, a non-inertial observer. So the twin paradox is not a paradox in the sense of logical contradiction, although it's a bit puzzling. There's a little section in the textbook about the twin paradox. Now we've studied time dilation. A related phenomenon is length contraction. And here's a picture from the textbook. It's figure 14. It shows the Earth, the Sun, and a spaceship which is traveling from the Earth to the Sun. It's assumed that the velocity is 0.8 times the speed of light. Of course, this is a science fiction example because there's nothing that can travel. There's no spaceship built by humans that can travel at 80% of the speed of light. So this is just a kind of a thought experiment. This is in the Earth frame of reference. In the Earth frame of reference, the rocket is traveling, let's say, 80% the speed of light, and the distance from the Earth to the Sun is 150 million kilometers. 150 million kilometers. Mega kilometers. Now here's the same system in the rocket frame of reference. In the rocket frame of reference, so the frame of reference in which the rocket is not moving, this is motion relative to the rocket. Well, relative to the rocket, the Earth is moving at 80% of the speed of light to the left. And of course, the sun is moving at 80% the speed of light to the left. In the Earth frame of reference, same as the sun frame of reference, the rocket is moving to the right. But in the rocket frame of reference, the Earth and the sun are moving to the left. It's the same speed, 0.8 times the speed of light.